In section 7.3, we look at general sequences and series. Let's consider the following example. Here we want to find the first four terms of each of the following sequences. So in the first example, we have an equals n squared, where n is equal to 0, 1, 2, 3, etc. So to find the first four terms, all I need to do here is plug in the numbers 0, 1, 2, and 3, right? That's the first four terms, into the formula. So let's go ahead and do that. So a naught would be 0 squared, which is 0. A1 would be 1 squared, which is 1. A2 is 2 squared, which is 4. And A3 would be 3 squared, which is 9. So the first four terms of this sequence are the numbers 0, 1, 4, and 9. And of course, it goes on from there. And so if you wanted more terms of this sequence, you would just continue plugging in 4, 5, 6, etc. into the formula. For the second example, they give us the formula a little bit differently. Instead of saying an, they write f of n. That's just notation. It's not really that important. But in this case, f of n is 1 over n plus 1. So again, to find the first four terms of the sequence, I'm going to plug in the numbers 0, 1, 2, and 3 into the formula. So f of 0 is 1 over 0 plus 1, which is 1. F of 1 is 1 over 1 plus 1, which is 1/2. F of 2 is 1 over 2 plus 1, which is 1/3. And finally, f of 3 is 1 over 3 plus 1, which is 1/4. And so the terms of this sequence in order are 1, 1/2, 1/3, 1/4, and again, this continues forever, but they only ask for the first four terms. Now, neither one of these sequences is arithmetic or geometric. These are just general sequences. So the things that we learned earlier about arithmetic sequences and geometric sequences, they don't apply to these two examples. In the next example, we're going to do the opposite. Suppose we know the first four terms of a sequence, and we're trying to write a rule for that sequence. So for part A here, we have the numbers 1, 8, 27, and 64. And if I'm going to write a rule for this sequence, I need to try to recognize a pattern. What is the pattern here? Well, if you think for a little bit, you might recognize that these are all perfect cubes. So if you take 1 and you raise it to the third power, you get 1. If you raise 2 to the third power, you get 8. 3 to the third power is 27, and 4 to the third power is 64. And we want the first number to correspond to n equals 0, the second number to correspond to n equals 1, the third number to correspond to n equals 2, and the fourth number to correspond to n equals 3. So the rule for my nth term is n plus 1 to the third power. Now, check your rule to make sure that it makes sense. So again, when n equals 0, do we actually get the first term of the sequence? Well, yes, because if you plug in 0, 0 plus 1 is 1, and 1 to the third power is 1. If n equals 1, do I get the second term of the sequence? Well, again, yes, because if n equals 1, 1 plus 1 is 2, and 2 to the third power is 8. Now, I just want to mention here that in this textbook, they like to start their sequences and series at n equals 0, but not all textbooks do it this way. In fact, in a lot of textbooks, they will start with the first term corresponding to n equals 1. So we have the same sequence here, But if this corresponds to n equals 1, and this one corresponds to n equals 2, and this one n equals 3, etc., your nth term is going to be a little bit different. In this case, it would just be n cubed, right? Because you're just taking this number and cubing it, right? 1 cubed, 2 cubed, 3 cubed, 4 cubed. So if we choose to start at n equals 1, the formula would just be n cubed. So just giving a formula for a sequence isn't quite enough. You need to also state that here are the starting values of your sequence here, and for the other one, here are the starting values. Okay, so I just want to point out that these two things are the same. We're just choosing to start at a different number for each one. Now for part B, we have the numbers 1, 1/4, 1/9, and 1/16. And first we need to try to recognize a pattern. And so 1/4 can be thought of as 1 over 2 squared. 1/9 is 1 over 3 squared, and 1/16 is 1 over 4 squared. And just to make sure the pattern makes sense all the way through, we could rewrite 1 as 1 over 1 squared. Now, if I want this first one to correspond to n equals 0, next one to correspond to n equals 1, etc., then the formula for my nth term would be 1 over n plus 1 squared. And again, this is because when I plug in 0, 0 plus 1 is 1, and that gives us 1 squared, which we have right here, right? So 1 over 1 squared. If n equals 1, 1 plus 1 is 2. 2 squared is what we have here, right? So again, because I'm starting at 0, I have to adjust what I'm squaring to make sure that it corresponds to the number that I have. And like the last example, we could also write this as an equals 1 over n squared if I choose to start at 1, right? So again, I can start this at 0, or I can start it at 1. If I start it at 0, I have to do it this way. If I started at 1, my formula is going to be a little bit different, a little bit simpler, actually. So when you're doing your homework, make sure you pay attention, because a lot of times they will prescribe to you where it needs to start, and that means that you'll have to have your formula written the correct way. For the third example, we want to try to find a rule for the sequence of numbers 1, -1, 1, -1, 1, -1, etc. So the way to think about this is powers of -1. So if you take -1 and you raise it to an even power, this is always going to be 1, right? So just think about that for a minute. If I take -1 and I raise it to the 4th power, this is -1 times -1 times -1 times -1. And this is 1 because every pair of negatives makes a positive when you multiply. So for that reason, -1 to any even power is always 1. Likewise, -1 to any odd power is always -1. Just take, for example, -1 to the 5th power, which is 5 factors of -1. Now, once again, every pair of -1s that you multiply together will be positive, but there's always going to be one factor of -1 left over, which makes your answer negative. So when you see a sequence of numbers like 1, -1, 1, -1, 1, -1, etc., you just need to think about these as even and odd powers of -1. So for example, I can think of the first 1 here as -1 to the 0. And then -1 can be thought of as -1 to the 1. And then the next positive one can be thought of as -1 squared. And then -1 cubed. And -1 to the 4th, right? And so this pattern works for all of these. And so the pattern is an is going to be -1 to the power n. And again, this is assuming that we start at n equals 0, 1, 2, 3. Now for the next example, they want us to simply fill in the table and plot the first 5 terms of the sequence. So here are the n values. We want to find f of n. Here is the formula. So this is just a matter of plugging stuff in. So to do f of 0, we're going to plug in 0 for n in both of those places. So we're going to have -1 to the 0 times 0 squared plus 1. Now we just talked about this. -1 to the 0 is +1 times 1. So that's going to be 1. F of 1, the next term of the sequence, we're going to have -1 to the 1 power times 1 squared plus 1. Well, -1 to the 1 is -1. And then 1 squared plus 1 is 2, so we get -2. F of 2 will be -1 squared times 2 squared plus 1. So this is going to be +1 times 5, which is 5. F of 3 is -1 to the 3rd power times 3 squared plus 1. So this is -1 multiplied by 10, which is -10. And finally, f of 4 is -1 to the 4th power times 4 squared plus 1, which is +1 times 17, which is 17. So now we're just going to take these numbers right here, and we're going to write those in the table. And one thing you should notice about these numbers is they alternate back and forth between positive and negative, positive and negative. And that is precisely what this factor does to a sequence. In fact, -1 to the n is usually called the alternating factor. Now, for the second part of this, how do you plot the terms of the sequence? Well, we're going to plot the terms by thinking of the x-axis as being the n axis, and the y-axis will be the f of n axis. And we're just going to plot these like points. So think of this point right here as being 0, 1. Well, where is 0, 1? Well, 0, 1 is right about here. And then we have the point 1, -2. So again, the value of n is 1, and the value of f of n is -2, so that would be right about here somewhere. And then we have the point 2, 5, so n equals 2, f of n equals 5, that's right here. And then we have 3, -10, which is down here. And finally, we have 4 and +17, which is up here. So what you should see about the values in this sequence as n increases is it kind of bounces between negative and positive, negative and positive, but it's also getting larger and larger. So if we continue, it's going to be like this. So that's what it means to plot the first terms of the sequence. You're just drawing a graph with points. Next, we look at an example of a sequence defined recursively. So what does that mean? Well, notice that they tell you that a0 is 1, so the first term of the sequence is 1. And then they tell you to get an, you're going to take 3 plus an minus 1. So what that means is to get an, you take the number 3 and you add it to the term of the sequence that came before n. Let's go ahead and take a look at the first several terms of this sequence. So to get a1, the formula says that a1 would be 3 plus a0. And that's going to be 3 plus 1 because they tell us that a0 equals 1. So that's 4. To get a2 is going to be 3 plus a1. Well, that's 3 plus 4 because a1 is 4, and 3 plus 4 is 7. To get a3, we're going to do 3 plus a2, and that's 3 plus 7, which is 10. So each time we're just adding 3 to the last term to get the next term. So A4 would be 3 plus A3, which would be 3 plus 10, which is 13. And then it asks you, what type of sequence is generated? Well, this is an arithmetic sequence, right? It's an arithmetic sequence because we are adding the same number every time to get from one term to the next, right? Notice that we're just adding 3 every single time. So because it is an arithmetic sequence, you should be able to find a rule for the nth term of the sequence that depends only on n. In other words, we don't have to write the rule recursively like they did here. We can write it directly. So what is the what is the nth term of an arithmetic sequence? So we should remember that an is equal to a naught plus n times d. So an is going to be a naught, which is the first term, which in this case is 1, plus n times the common difference, and the common difference in this problem is 3. So this is 1 plus 3n, or you can write that as 3n plus 1. So notice that if we had been given an equals 3n plus 1, where n equals 0, 1, 2, 3, etc., you would get the same terms for this sequence, right? So if n equals 0, 3 times 0 plus 1 would be 1. If n equals 1, 3 times 1 is 3, plus 1 is 4. If n equals 2, 3 times 2 is 6, plus 1 is 7, etc. So this would generate the same terms of the sequence that we got up here. Okay? But notice the different definitions. This is a recursive definition, which meant to find the next term, we had to know what the last term was. This is a little bit disadvantageous, right? It's much better to have a formula for an that only depends on n. Because then if I want to find the 50th term, I don't have to find the first 49 terms, right? Here I would have to know the 49th term to get the 50th term. Here I don't. If I want the 50th term, I just plug in 50, right? So this is just an example to get you thinking about recursive definitions versus explicit definitions. So next we have a very famous recursive definition. This is called the Fibonacci sequence, and for that reason we abbreviate these terms F0, F1, etc. So the way the Fibonacci sequence works is the first term of the sequence is defined to be 1. The next term of the sequence is also defined to be 1. And then from that point forward, if I want to get the next term, I have to add the previous 2 terms. So to get Fn, I have to add Fn minus 1, which is the term right before Fn, and I have to add Fn minus 2, which is the term right before Fn minus 1. So what that means is if I want the second term, well, it's really the third term, but we call it F2. If I want F2, I got to do F2 minus 1 plus F2 minus 2. So that is F1 plus F naught, right? Well, F1 and F naught are 1 and 1, and 1 plus 1 is 2. If I want to get F3, I have to do F3 minus 1 plus F3 minus 2. This is F2 plus F1. So to get F3, I have to add F2 and F1, which are these two. So that would be 3, right? 1 plus 2 is 3. So basically, to get the next term of the sequence, I'm just adding the previous 2 terms. So to get the next term here, 2 plus 3 is 5. And then 3 plus 5 is 8. And 5 plus 8 is 13. And 8 plus 13 is 21. And we can keep going on like this forever. This is called the Fibonacci sequence. And you can only describe the Fibonacci sequence using a recursive definition. There is no way to give a general formula for this like we did in the previous example. Finally, we end with the nth partial sum of a sequence. And so when you see this sigma notation, sigma just means summation. So if we see that sigma of ai, I equals 0 to n minus 1, it means you're going to plug in the numbers 0, 1, 2, 3, etc. in for I, and then add them all up. This is referred to as the nth partial sum. Let's go ahead and take a look at a couple of examples here. So in the first example, we're asked to calculate the sum from starting at I equals 0, stopping at I equals 4, of I squared. So to do this, we're going to take the number 0 and we're going to plug it in here for I. So that's going to give us 0 squared. Then we go to the next number. The next number after 0 is the number 1. So we're going to add 1 squared. And then we go to 2. Plug that in. We get 2 squared. And then 3 squared. And finally, 4 squared. So we stop when we reach this upper number here. And if I want, I can add these up. This is just 1 plus 4 plus 9 plus 16. And if you add these numbers up, you get 30. For the next one, we have the sum I equals 0 to 3 of negative 1 to the I power times 2I plus 1. So again, we're just going to start by plugging in I equals 0, and then I equals 1, I equals 2, and I equals 3. And then when we plug those in, we're going to figure these out and then add them up. So when we plug in 0, we get negative 1 to the 0 times 2 times 0 plus 1, plus, then we're going to plug in 1, we get negative 1 to the 1 times 2 times 1 plus 1, plus, when we plug in 2, we get negative 1 to the 2 times 2 plus 1. And finally, we have negative 1 to the 3 times 2 times 3 plus 1. Now to add these up, we'll just do the math. Negative 1 to the 0 is 1. 2 times 0 plus 1 is 1, so we have 1 times 1. The next term, we have negative 1 to the 1, which is negative 1. And 2 times 1 plus 1 is 3. And then negative 1 squared is 1 again. 2 times 2 plus 1 is 5. And finally, negative 1 times 2 times 3 plus 1 is 7. So this is 1 minus 3 plus 5 minus 7. And if you add these up, you get negative 4. So this is what we call the nth partial sum of a sequence. It's not terribly difficult. You just want to get comfortable with this notation. So again, you just start at the bottom number, you stop at the top number, and you make sure you hit every integer in between the two, plugging them in one by one, and then adding up each term of the sequence.